Welcome to the Explainer. Today, we're tackling a classic algorithm that, believe it or not, powers everything from your map app to the internet itself. So how does it do it? Well, it uses a really clever set of rules to solve a kind of puzzle. And by the end of this explainer, you're going to understand exactly how it works. Okay, let's dive into this. All right, so here's our puzzle. It's a simple network of 4 locations, or nodes as we'll call them, numbered 0 through 3. Our one and only goal is to find the absolute shortest path from our starting point, node 0, to every other node on the map. Now, this table right here, this is our map. The numbers show the distance, or weight, between any 2 nodes. So for example, getting from node 0 to node 1 has a weight of 2. And if you see a 0 between 2 different nodes, that just means there's no direct road connecting them. To solve this, we only need 2 super simple tools. First, a way to track distances, and second, a way to remember where we've already been. That's it. So this first tool is basically our scorecard. And the keywords here are so far. This list isn't set in stone. We're going to be updating it constantly as we find shorter and shorter paths. Okay, so we're starting at node 0, right? The distance to get to yourself is, well, it's 0, obviously. But for everywhere else, we haven't explored anything yet, so for now, we'll just set their distances to infinity. It's really just a placeholder for we have no clue yet. And this is the secret sauce. The entire algorithm comes down to this simple 4-step process. We're just going to repeat it over and over. Pick, look, update, lock. Let's see it in action. All right, round 1. The first step of our mantra is pick. We need to pick the unvisited node with the smallest distance. Right now, that's a no-brainer. It's node 0 with a distance of 0. Step 2. Look. So we look at our map and see what's connected to node 0. Looks like we can get to node 1 for a cost of 2 and to node 2 for a cost of 5. Now for step 3. Update. Is a path of 2 to node 1 better than infinity? You bet it is, so we update our scorecard. Same deal for node 2. A path of 5 is way better than infinity, so we update that too. So here's where we stand after 1 round. We've got our first real distances recorded. And now for the final step in the cycle, lock. We mark node 0 as visited. We are done with it. We never have to look at it again. Okay, here we go again. Mantra time. Step 1 is pick. We look at the unvisited nodes, that's 1, 2, and 3. Their distances are 2, 5, and infinity. The smallest one wins, so we're picking node 1. Next up, look. From our new spot at node 1, we can see it connects to node 2 with a weight of 1 and to node 3 with the weight of 4. We completely ignore node 0 because remember, it's locked. It's old news. And now for the update step. This is where the magic really happens. To find the new path length, we take the distance to get to our current node, which is 2, and add the new leg. So for node 2, that's 2 plus 1, which equals 3. Is 3 better than our old distance of 5? Yes, it is. We found a shortcut. So we update our scorecard. So our scorecard gets an upgrade. This is that greedy part of the algorithm I mentioned. It always goes with the best path it knows so far and then checks if that leads to even better shortcuts. Okay, now we lock node 1 as visited and we move on. You know the drill by now. Time to pick again. Our unvisited nodes are 2 and 3. Looking at the scorecard, node 2 has the smaller distance of 3, so that's where we're going next. So from node 2, we look and see we can reach the unvisited node 3 with a weight of 1. To get the total path, we take the distance to node 2, which is 3, and add this new step. 3 plus 1 gives us 4. The old distance to node 3 was 6, so 4 is a huge improvement. Another update? Fantastic. We change the distance to node 3 to our new best score of 4. We lock node 2, and now we are on the home stretch. Only 1 node left. Okay, last stop, node 3. We pick it since it's the only one left, but when we look at its neighbors, we find they've all been visited and locked already. That means there's nothing new to check, no updates to make. The algorithm is done. And there it is, our final scorecard. This shows the absolute shortest distance from our start, node 0, to every other node in the network. We've officially cracked the puzzle. This summary table really tells the whole story of our journey. You can see exactly how the distances were discovered and improved step by step as the algorithm got smarter and smarter, finally leading to that optimal answer. So, from the internet traffic routing data to your screen right now, to social networks figuring out how you're connected to other people, this fundamental concept of pick, look, update, lock is quietly shaping the efficient world all around us. Thanks for watching.